Hello, everyone, and welcome to week number 18 of Qubit by Qubit's Intro to Quantum Computing. Today, we're going to be talking about superdense coding. So superdense coding is, I would say, sort of the first full, real, nothing held back quantum algorithm that we learn in this course. So for a while now, we've been looking at some simple quantum circuits on IBM Qiskit, that kind of thing. Those are all good and valid, but for this is the first time where we're learning something that is, I would say, sort of truly, well, possibly useful as far as we know, and is going to get a little bit more complicated. So as we sort of shed off the training wheels and start going with a full-fledged quantum algorithm, well, number one, I'm really excited for that. I hope you are too. Number two, though, I'll just remind everyone that I am very much open to answering questions as we go through this lab. Please feel free to use the chat function. Direct message me if you're not comfortable with putting your name out in the public, and I won't mention your name. And if I don't have a chance to answer your questions here, certainly feel free to post them on Piazza. One of the reasons I say this is that I believe a solid understanding of superdense coding will set you up very well for pretty much all of the algorithms that we'll learn throughout the rest of this course. It's not to say that this is simple. I think it's tough to get your head around what's going on here. But once you do, that is all of the foundation you need to start understanding more quantum algorithms. So without further ado, let's get right into it. Quick program for today. We will start off with the Canvas attendance quiz, as always. Then we will do our pre-lab Zoom feedback. I didn't really have any questions from last week, although if you do have questions from last week's content, feel free to throw them in the chat. Instead, we will spend the majority of today's time on the actual lab content itself. We have a bit of a longer notebook to go through. There's no slides. It's just going to be on Jupyter Notebook, coding the whole time, and hopefully answering your questions as we go along. Okay, so let's do the Canvas attendance quiz real quick. Lab number is 1, as always, and today's password is 1690. The question we're asking is for you to please rate the level of difficulty of the work in this course. So this is going to be different, depending on what stage of life you're in, but try to relate it to sort of the level of difficulty of, I guess, academic work that you best remember at this point. As always, there's no correct answer here. This is more just for us to gather some information. Please do make sure you fill out the quiz to get counted for lab attendance. And I will also open the chat. So if you have any issues with the Canvas attendance quiz, please feel free to throw that in the chat. Okay, so let's do the pre-lab Zoom feedback. I'm actually quite curious to see this one. I'm wondering how you all found this week's lecture. Okay. Generally pretty good, although I will say that this is lower than what we usually see. Not surprising at all. I think, as I said before, superdense coding is not the easiest thing to get your head around, but hopefully I can help clear some of these things up as we go forward today. Before we charge on, does anybody have any questions from last week's material? We'll hold off on any superdense coding questions because I will hopefully answer a lot of those in the course of the lab. But for right now, any questions on last week? Okay, so yeah, difficulties with superdense coding, totally understandable. We will get to that. Okay, so I will go ahead and end off this poll and just share the results. So somebody says, I had to miss the lecture this Sunday. Will I still understand things today? I believe so, yes. So I will be teaching everything, sort of assuming you know everything up to this Sunday's lecture, but not including this Sunday's lecture. So we will do a full review of superdense coding. I'll talk about why it works theoretically, and then we'll also talk about how to code it in Qiskit. The attendance quiz is still not opened. Oh, interesting. Is anybody else having that problem? Okay, so most people are saying it worked. To the one student who said that the quiz was not open for them, if it's not working for you, no worries at all. If you are running into issues with it, just email student@qubitbyqubit.org, and they will be able to help you out. Don't worry about attendance. I'm sure they'll get it figured out. Okay, so somebody also asked, there was something about noise in the IPyNB file in the last homework IPyNB file. I didn't get that part. So perhaps we can talk about that in the optional content. I don't have a fast answer for you just because I didn't look at the homework IPyNB from last week. But certainly in the optional content, I can take a look and hopefully answer some questions there. Somebody says, unusually, the math was easier to understand than the application covered in this week's lecture. Yes, yeah. Well, I think the point of this course and the way that we're trying to structure it is hopefully you have all of the sort of foundational math and physics and probability and all that kind of stuff that you technically need to understand superdense coding. So the difficult part here is going to be more of the sort of overall application, how it all fits together. So yeah, I definitely feel that. Okay, last question of the homework. Yeah, so I'm happy to go over some of the homework from last week. I'm going to suggest that we save that till the optional content, though. Awesome. All right, so let's get going with superdense coding. I don't think I have any more slides. Let me just double check. Okay, well, I guess there's a quick summary. We will, of course, spend most of the lab implementing superdense coding on Qiskit. There's a quick overview of all the things we'll be covering, but of course, I'll go into more detail. And then the optional content today is preparing the psi minus Bell state, which is kind of continuing on the tradition from the past couple of weeks. We learned how to create phi plus, we learned how to create phi minus. We will look at psi plus. Just keep in mind, try and keep in mind all these different Greek letters. We'll look at psi plus today, and then we will look at psi minus also today in the optional content. So then you'll have seen sort of a full explanation, hopefully, of all the different Bell states. Okay. Cool, so I'm going to go ahead and switch over to IBM Qiskit. And hopefully, I think this was the lab where I accidentally showed the answer key last time. Hopefully we don't do that again. Okay, awesome. So you should all be able to see my dashboard at this point. Let's just confirm that that's all good and working. And I will also zoom in. Sorry, I forgot to do that ahead of time. Let me know if this is still too small for anybody to see. Okay, so here I am on my desktop. Now, one thing that has changed, obviously, from the last time that we looked at IBM Qiskit is, unfortunately, there's been a UI update. So none of the functionality that we're concerned with has changed. Everything still works the same. Somewhat unfortunately for us, though, IBM decided to push out an update to their user interface. So everything looks pretty dramatically different. I personally think it's a good update. I think that it makes things easier to look at now. It's more convenient to navigate, but it is going to look different. So I'll just kind of go over that. Oh yeah, the Canvas code, I believe, was 1690, and I will go ahead and add that up here. So this is going to be hopefully the new equivalent of putting things in the bottom right of the slides. I'll just try to remember to annotate the access code up here on the top of my screen when I start sharing. Okay, yes, so new user interface. Oopsie, need to get out of this. New user interface. I guess the main things to understand is they've actually made it more clear where the two things we care about are. So the circuit composer that was previously in the sort of left-hand menu is now just this big blue launch composer button. And the quantum lab is now this big blue launch lab button. You'll also notice that I have some like recent work links here. So once you've uploaded an IPyNB file, you can just jump back to your work nice and quickly right there. Now for me, I'm going to go through the full process though, so I show you how to upload a notebook as well. So to upload a notebook, you go to Launch Lab. It's going to give you a screen that looks like this. You might not have a recent notebook appearing over here on the right-hand side. I do, because I was preparing for this lab previously. To upload a notebook, though, you're going to click, oh, my interface is taking a while to load. That is one thing I've noticed. This UI seems to be a little bit slow. But once you have your Jupyter notebook loaded and everything, then it seems to be okay. So hopefully this won't be too much of an issue. So the lab attendance code, I've just put in the top of my screen here, right next to IBM Quantum Lab. It's 1690. Okay, so somebody direct messaged me, if you don't mind, can you please tell me where we use API tokens for the IBM Quantum experience? I believe the API, so the API token was shown on our dashboard screen. No worries if you didn't see it. This is not something we need for today. But I believe those are used for running on actual quantum computers from Qiskit. I'm actually not 100% sure, but that would be my guess. Okay, so my UI has loaded here, so that's good. To upload a file, or to upload an IPyNB file, you're just going to click this little symbol here. So it no longer has any words next to it, but you would click this, it pops up with a file selection dialog. You select your Python notebook, it should appear here. And then to open it, you're just gonna click it. And then this UI on the right is gonna take a while to load. Okay, so once you've loaded this, you can close this file menu by just clicking that file button here. It's just a toggle. So I'm going to do that. So we have our full nice screen here to work with. And now let's get started with today's notebook. So a quick overview of what we're going to be doing today. In the introduction, I'm going to talk about the full process of superdense coding. So we're going to look at the whole algorithm sort of from a higher level and make sure we understand what each of the steps is supposed to do. Then in the second part, we're going to code each of the steps, right? So we have it broken down into 5 pieces here. We'll learn how to represent each of those 5 steps in Qiskit. At the end, we're going to sort of put it all together. So we'll have one big code block right at the end, which sort of does the entire circuit for us. We will go ahead and simulate that circuit to see it work. And then we will talk a little bit about the difference between superdense coding and quantum teleportation. So lots to cover today. Let's go ahead and get started. So first things first, as always with these notebooks, we need to import stuff. So today we actually don't need that many things. We just need these. So again, I'm just going to click this cell and then click the run button. And when we see a number here, that means that our cell has run. Okay, so let's do a brief introduction to superdense coding. The basic idea of superdense coding is that you want to send a message to somebody else, right? And any message, English, numbers, whatever, can be translated into binary. So there's actually an example of this, I think, on this week's homework. But for now, we'll just take it for granted that you want to send a message and your message consists of zeros and ones, right? So the example here is maybe you want to send the message 00110101, and maybe you've previously agreed that this is the code that means let's go get ice cream or something, right? And there could be a whole bunch of different combinations of zeros and ones that mean different things. So the question posed here is, how many bits of information do you need to send, right? Now, we are used to sort of instantaneous, hyper-fast transmission of messages on the internet. We take it for granted that you can upload and download many megabytes every second, right? But in this scenario, we want to really look at how expensive our communication is. How many bits can we actually translate, or do we actually need to transmit, I should say, to get our message across? In this case, we've decided on an 8-bit message. If you just count the number of bits here, there's 8 of them. And so we would need to send 8 bits to our friend to get this message across. At a high level, superdense coding is a quantum algorithm where instead of sending classical bits, you're going to send qubits to the other person. Now, the message is still written as classical bits. This is where it starts to get confusing. So I'm going to try and go through things very clearly. The message is still classical bits, but instead of sending classical bits as, for example, pulses down a wire or something like that, we're going to send qubits. Why would we do this? Well, because in superdense coding, you only need 1 qubit for every 2 classical bits of information. Whereas we would need 8 classical bits to send this message, superdense coding lets us send it with only 4 qubits. Now, transmitting qubits is currently quite difficult, and so it doesn't really make sense to use this algorithm in real life yet. But at least in theory, this would be a significant savings, right? It means that if you wanted to send a 1 gigabyte file to your friend, well, now you would only have to send sort of 500 mega qubits, right? You only have to send something that's half as large to get the same message across. Okay, so let's look at how this works in particular. The first thing to review is the Bell states. So these are the same definitions that we've seen before, phi plus, phi minus, psi plus, psi minus. And they are just definitions, right? We're not really going to talk about more why they're called these things. Just remember these names for these different states. Now, in superdense coding, at a high level, we're going to use these entangled states to transmit our information. Usually when we talk about these kinds of, well, any kind of algorithm in cryptography or teleportation, that kind of thing, we're going to talk about 2 parties named Alice and Bob. And sometimes there's going to be a third one called Charlie. I'll mention that one briefly in a little bit. But basically, it's about Alice trying to send a message to Bob, right? Just simple names, A and B. And that's how we're going to sort of phrase all of our discussion with superdense coding. Now, to sort of motivate the rest of our discussion, I want to ask this question to you. How many bits of information does a Bell state carry? Right? So if we had 2 qubits, right? We have 2 entangled qubits, and they are in some Bell state, and we could somehow find out which Bell state that was, how many classical bits of information does that give us? In my opinion, the easiest way to think about a question that asks, how many classical bits of information are in or are contained in X is to think about how many possibilities there are. So if we know our 2 qubits are in a Bell state, there's 4 possibilities. And if we have some way to narrow that down and figure out that we are in this particular Bell state, that gives us sort of a 1 in 4 reduction in uncertainty, right? Previously, we had 4 possibilities. Now we're down to 1. And so if we go from the number of bits required to represent 4 possibilities down to just 1, that's 2 bits of information, right? Because 2 bits lets you represent any number from 1 to 4, or I guess I should say from 0 to 3. Same deal. So a Bell state, if we have 2 entangled qubits, we know it's in a Bell state, and we can somehow figure out which Bell state we're in, we get 2 classical bits of information. One way to think about this is you can think of these 2 bits representing, first, whether our 2 qubits are going to be the same or different, right? In other words, are we going to be in the phi states or in the psi states? The second bit of information is whether we're going to be in a plus state or a minus state, which is the same as asking, what is the relative phase here? So there's a couple ways of thinking about this. But again, the basic takeaway is a Bell state contains 2 classical bits of information. Okay, so let's do a quick review of superdense coding. As you might guess, the way that we're ultimately going to do this algorithm at a high level is somehow we're going to measure a Bell state at the end. Because of what I just said, when you measure a Bell state, you get 2 classical bits of information. But in order to sort of transmit that Bell state, we're only going to need to send 1 qubit. So at a high level, we're going to send 1 qubit that sort of completes the Bell state for Bob. Bob is going to measure that Bell state, and from that measurement, get 2 classical bits of information. In a little bit more detail, here's what it looks like. The algorithm has to start with Alice and Bob being together, or with a third party called Charlie that creates an entangled state and sends 1 qubit to Alice and 1 qubit to Bob. So this preparation step, we don't usually count as part of the algorithm. And so, when we say that you only have to transmit 1 qubit to transmit 2 classical bits, that's the whole point of superdense coding. We're not including any transmission that has to happen to set up these 2 initial states. right? So the way that I like to think about it is Alice and Bob meet together at some point. They know that in the future, they're going to have to transmit some message. But for now, they just create a bell state. So they're going to create the phi plus state, and each of them will take one of those qubits and go off to their homes, right? Now, that's step two. I guess I just said they have to travel far away, right? And so it's this transmission from Alice to Bob. Now that they're no longer together, they need some way of transmitting a message to each other. Then in step three, Alice is going to encode her classical state in her qubit. So she's going to have some 2 classical bit message that she wants to send to Bob. And she's going to somehow do something to her qubit, and we'll learn what that something is. She's going to do something to her qubit that encodes that information in the entangled state. Then she sends her qubit to Bob. So this is the step where we're sending 1 qubit. And Bob is going to go through a final step that we call decoding. So this is going to be a series of gates and measurements to get 2 classical bits at the end of the story. And ideally, the 2 classical bits that Bob gets here are going to be the same as the ones that Alice encoded back here in step 3. Okay, so I'm not going to spend too much time talking more about the high level because I personally think it helps to just go through the whole algorithm and see it together all at once first. But hopefully I will have some more time at the end to sort of clarify any misconceptions with how the algorithm works at a high level. So let's dive into each individual step of this algorithm. Step 1 is preparation. Now, preparation we have seen before. This basically consists of creating the phi plus state. That's it. Alice and Bob are together. We don't have to worry about any sort of transmission or anything like that. We have both qubits, and we just want to prepare the phi plus state. Now, I'm not even going to go through this again because we have seen this circuit, I guess, 2 weeks ago now. I guess just to review quickly, though, we use the quantum circuit command with the number of qubits to create a blank circuit. And then we do circuit name.gate name to apply gates to our circuit. To create phi plus, we learned that you do an H gate on qubit 0, and then a control X gate on qubits 0 and 1, and you get a circuit that looks like this. And so what's nice about this is we start off with our qubits in the states 0, 0, right? Qiskit always initializes our states in the state 0, 0. By the end of this, our 2 qubits are going to be in the state phi plus, which means they're going to be in this state. 50-50, 0, 0, or 1, 1. So if you need a review of how this circuit works, no worries. Feel free to go back and watch, I believe it was 2 weeks ago, we talked more about the phi plus circuit. Now, there is a note here about the role of Charlie. So I believe in the homework, they do talk about this third party Charlie. Charlie's only job is to create a bell state and send the 2 qubits to Alice and Bob. It's pretty much the same deal as if Alice and Bob just meet together first, create their bell state, and then go apart. It's just different ways of looking at the same problem. I hope this doesn't lead to too much confusion because it's honestly not a super important point. Okay, so to make things a little bit easier later on, we're going to put this first step inside a function. And you'll see that for several of the steps in this algorithm, we're going to create functions as we go so that the final thing, when we put it all together at the end, is a little bit shorter and easier to look at. So I'm going to give myself a code block here. Now, defining functions for quantum circuits is not something, I believe, is not something we've seen before, but it's no different from just defining a regular function in Python. So I'm going to start off with the def keyword. So that just defines a function. We'll call this create bell pair. Now, the only sort of complicated part here, I guess, is that as an argument, we're going to take the quantum circuit itself. Actually, so I'll call this circ, just so it's more consistent with the naming we've been using. So this is going to be passed in as an argument. We'll assume that somebody has created a circuit using this quantum circuit command, and they're now giving us that variable as an input to our function. Now, what do we have to do to create a Bell state? Well, we know it's just this circuit. So I'm going to do, again, circuit name dot gate name, target qubit, circuit name dot gate name, target qubits. And that's it. So this is going to sort of take an initial quantum circuit, and it's going to add some stuff to it, which we know is a Hadamard and a CNOT gate that makes the circuit output phi plus. Okay, I'm just seeing somebody says, can you write the code further up because I can't see because of the transcript? Yes, absolutely. I will try to write code up here. Thank you. Okay, so I'm going to go ahead and run this code block. So nothing pops out here, nothing gets printed, but now we have defined a function that's going to be helpful later on for constructing our full superdense coding circuit. Okay, on to step 2. So step 2 is that Alice and Bob travel far away. Now, there's not really anything we have to do to the circuit in this case. I am going to do one thing, though, to just give us a visual cue of what's going on. So again, Alice and Bob traveling far away, there's no like gates we have to apply that simulate this. What I am going to do, though, is add something called a barrier. So a barrier is something in Qiskit that is just a visual indicator between two parts of a circuit. It doesn't do anything, right? Like it doesn't change your quantum circuit at all. It's purely a visual cosmetic marker of something. So in our case, we're going to use this as a marker for when qubit movement happens. Now, I'm going to go ahead and add a code block here. And then I'll just show you how this should work. So I'll use our circ phi minus, or sorry, phi plus that we had from before. And just like most things in Qiskit, it's always circuit name dot, and then we use dot measure, dot gate name. Here it's going to be dot barrier. Sorry, I'll type further up. Circuit name dot barrier. Okay, so once I specify that, I'm going to go ahead and draw our circuit again. And then we'll click run. Oh, I guess I already applied a barrier. What did I miss here? Huh. I'm not quite sure what happened there. I think that's, sorry, let me just do some quick live debugging here. I think it's because I forgot to run this. Yeah. Okay. Sorry about that. That was just me not running my cells in order. I guess I should note this, I guess. As I make mistakes, I'll try and explain how to debug them. Oh, somebody says, can I let waiting students into the meeting? Yes, absolutely. I thought actually, I don't think there should be. I don't see any waiting students. Because I should have turned off the wait room functionality when the lab started. So hopefully, maybe if they like try rejoining, it'll work. I'm not 100% sure. That sounds like a Zoom issue to me. So sorry, back to this mistake that I made with these barriers. Oftentimes the order that you run cells in can lead to errors like this. So in this case, when I was preparing for today's lab, I added this barrier, right, to our circuit, and I forgot to rerun the initial circuit. Right, so I forgot to sort of reset it back to normal. And so when I added another barrier, there were two barriers showing. One thing that you can do is you can go up here to kernel in the menu, and you can do restart and clear output. So I should have done this probably before I started the lab today, and usually I remember to do it. But this just basically clears everything out of the Python memory in your notebook. It clears all of the outputs to make sure that you don't have any of this sort of interference happening. So just a quick tip there. But anyway, I think this should be good for now. Let's see. I'm just seeing if there's any sort of quick questions. If I'm not answering your question right now, it's nothing personal. Feel free to post it again when I get to a proper break period. One person saying, not able to look at the content in my IPNB copy. My copy might be a little bit different. than yours, like in a different order, but it shouldn't be too different. There is one difference later on that I'll point out, but we haven't gotten there yet. Can I explain the barrier once again? Yeah, so this barrier command, it literally just does this. It puts this sort of visual indicator into our quantum circuit. It doesn't change our qubits at all. It doesn't act as a gate. It's purely visual. So I'm just using it here so that we kind of make a note for ourselves that, okay, this is where Alice and Bob are going to go off and travel far away, right? And then we'll keep adding on to this circuit. It's just to remember where this step 2 happens. That's really it. Okay, so the question about how many bits of information does a Bell state carry? I answered that earlier, so I'm not going to go over it again, but if you do want to watch the lab, it is recorded. So somebody says, shouldn't, okay, yeah, this is a good question, actually. So in this function I defined earlier, this create Bell pair function, they said, shouldn't I be returning the circuit after this function? Now, if you are new to programming, this concept might sound foreign, and that's okay. But there is a concept of sort of local modification of variables. In this case, I believe it should work. I guess we'll find out if it doesn't. I'm pretty sure it does, though. And the intuition, I guess, behind that is that this value here is like a pointer. So if you've taken a programming course in C or C++, you probably know what pointers are. In Python, everything is passed by value. This is a pointer being passed by value. And so anything we do to it in here is going to affect the original object. Again, no worries if those words are unfamiliar. That's more programming stuff. But long story short, this should work for what we're doing here. Okay, so back to the main narrative of superdense coding. Just to do a quick review of where we're at. We constructed our phi+ state, right? That's something we learned how to do before. That is step 1 of superdense coding. Step 2 is now to have Alice and Bob travel far away. There's nothing we have to do to our circuit for that step. So instead, we add this purely cosmetic element called a barrier that's just going to act as a visual reminder for Alice and Bob traveling at this point in the algorithm. Another thing I should mention, by the way, when we talk about algorithms in quantum computing, it's pretty much the same thing as a circuit. Maybe you've already realized this, but circuit and algorithm are kind of interchangeable. And so when we talk about executing an algorithm and like earlier stages in the algorithm, later stages in the algorithm, that's basically talking about running a quantum circuit and things that are earlier or further to the left in the quantum circuit and later or further to the right in the quantum circuit. So circuit, algorithm, really kind of the same idea. So with steps 1 and 2 done, let's move on to step 3. So now, Alice and Bob are in 2 separate parts of the world, right? So say one is in Spain and one is in China, right? And they have 1 qubit each from this entangled pair. And now they want to send 2 classical bits of information by Alice sending her 1 qubit to Bob. How do we do this? Well, first step is for Alice to encode her message. So Alice has some 2 classical bit message that she wants to send. Okay, so to sort of remember this, we're going to define some relationships. Depending on the state that Alice wants to send, the bits that Alice wants to send. If she wants to send 00, 01, 10, or 11, she is going to prepare a different state. So how exactly does this work? Well, let's first look at the first case, right? If Alice wants to send the message 00, that is a 2 classical bit message. Her goal in this encoding step is to turn the entangled pair that her and Bob have into the corresponding state here, which in this case is phi+. Now, the state that they have is already phi+, and so in fact, if Alice wants to send 00, she doesn't do anything in this step. This step is blank. But if she wants to send one of the other 3 messages, she has to do something to her qubit to transform the entangled state that her and Bob share into one of these three states. We already looked at how to create phi minus last week. And if you remember, the difference with phi minus was we added a Z gate. Instead of having H and then C naught, we did H, Z, C naught, right? And so the interesting part about this is that the difference between phi plus and phi minus, it only differs by a gate on the first qubit, qubit 0, right? And so Alice could, in theory, do something only to her qubit and have it change the whole entangled state, right? The state of their two qubits together would change from phi plus to phi minus by her performing a gate only on her own qubit. Now, this is kind of the magic of entanglement, where applying a gate to Alice's qubits over here in Spain is going to modify the shared state in China as well, right? Now, there is one kind of technicality we have to discuss here, which is the phi minus circuit. Now, in last week's lab, when we looked at the phi minus circuit, we saw something like this. Right? We saw, as I said before, H, Z, C naught. And we used the state vector simulator. We confirmed that this did what we wanted, et cetera, et cetera. For this, it's going to be easier to see what's going on if we move the Z gate after the C naught. Even though this circuit looks different, it's in fact mathematically the exact same. You can prove that using matrices and linear algebra and the tools that we learned with tensor products last week. And I'm happy to sort of show that in the optional content if people are interested. But I think the best way to think about it is to try and remember the intuitive understanding for a C naught gate. Remember that a C naught gate sort of has this conditional behavior, right? If your control qubit is 0, do nothing. If your control qubit is 1, apply a gate to the target. But in all cases, all 4 possibilities, you don't modify the control qubit, right? The only thing that might change is the target qubit. And so we can freely move this Z gate to either side of the C naught gate because this little control symbol here doesn't actually change the control qubit, right? It signals what the C naught is doing, but it doesn't modify the control qubit. And so we can move the Z gate to either side of it. That's a hand-wavy explanation, but I do think that's the best way to sort of intuitively think about why this works. Somebody said, can you clarify which bit is shared or entangled in the Bell states? So in the Bell states, we have a 2-qubit system, right? Because the Bell states are written in terms of these basis elements that have 2 bits, 0, 0, 1, 1, 0, 1, 1, 0. So the whole Bell state is 2 qubits, and it's those 2 qubits that are entangled. I'm not 100% sure if that's what you're asking here, but hopefully that clarifies. Okay, so let's return to this discussion of encoding. Again, the point here, just to sort of take a step back, is Alice and Bob have the phi plus state shared between them. They've gone apart, so now Alice can only do stuff to her qubit, but somehow we want her to be able to transform their shared state into any one of these 4 based on the message Alice wants to send. So again, if she wants to send 0, 0, they already have the phi plus state, so she doesn't have to do anything. If she wants to send 0, 1, well, what we just saw is that she can apply a Z gate to her qubit even after the C naught gate, and they will end up with phi minus shared between them. So the final step here is to look at how Alice would transform their shared state into psi plus or psi minus. So somebody asks in the chat, does the messages Alice might want to send, are they represented using 1 qubit, or are the messages combined with Alice's qubit and Bob's qubit? Good question. So we will get there later in the algorithm, but at the end of the day, Bob is going to have both qubits to come up with his answer. So this can be a little bit confusing because the whole selling point of superdense coding is, oh, you use 1 qubit to transmit 2 classical bits of information. Actually, you need 2 qubits The difference is that only one of those qubits is transmitted, right? So at the end of the day, Bob is going to need 2 qubits to get those 2 classical bits of measurement, but only one of them will have to be sent by Alice, right? Bob was holding on to one of them the whole time. Okay, so let's return to this question then of how we create the psi plus state. Let's do that as our first example. Kind of like what we saw with the phi minus state, the easiest way to figure this out is to look at phi plus and psi plus and try and figure out what the difference is, right? So for the phi minus state, we saw that the difference was a minus sign. We wanted to apply a minus sign to the 1 state and leave the 0 state unchanged. In this case, let's remind ourselves that psi plus equals this. What is the difference between this and phi plus? Is there any gate that would perhaps introduce this difference for us? So have a think about that. Remember, phi plus is 1 over root 2 ket 0, 0 plus ket 1, 1. And we want to somehow turn that into this. What single qubit gate would do that for us? Cool. So some people are direct messaging me. Yeah, I don't have a proper Zoom poll for this, but yes, it is the X gate. So the intuition here is that we start off with ket 0, 0 plus ket 1, 1. And in comparing that with this, we notice that only one of the qubits has changed, right? So in this case, the first qubit looks to be staying the same, but the second qubit has been flipped. Where we used to have 1, 1, now we have 1, 0. Where we used to have 0, 0, now we have 0, 1, right? And so you could view this as simply flipping that second bit. Now, I'm going to push us one step further. You could also view it as flipping the first bit, the first qubit. To do that, you would just have to flip, you would have to exchange your 2 terms. So for example, if we started with 0, 0 plus 1, 1, and I flip the first qubit, we're going to get 1, 0 plus 0, 1. But notice 1, 0 plus 0, 1 is just if you exchange these 2, right? And addition, you can swap things in addition, it doesn't matter. And so indeed, psi plus can be created by either swapping the first qubit or the second qubit with an X gate. Now, because we are Alice in this scenario, we are going to apply the X gate to the first qubit, qubit 0, the one that's with Alice. Okay, so let's go ahead and create our circuit here, just to try this out. I'm going to give myself a code block, and I will call this one circ psi plus. So note the spelling difference here. I know it's a bit confusing. We'll use the quantum circuit keyword. This is a 2-qubit circuit. It's going to look very similar to phi plus. So we'll do circuit name dot gate name. So we'll start off the exact same way. Hopefully that's starting to look fairly familiar, this phi plus circuit. And then we're going to apply an X gate. And remember I said it should work if you apply to either qubit 0 or qubit 1. In this case, we're Alice, so we're going to apply it to qubit 0. And then final step, as always, is to draw our circuit to make sure everything, sorry, I keep forgetting to do the typing higher thing. Our final step here is to draw the circuit to make sure everything looks as we expect. So with my cell highlighted, I'm going to click run. There we go. This is indeed what we're expecting. And notice this looks, I don't know if I can get it all on the same screen, not quite, but this looks very similar to our phi minus, right? In phi minus, we did our phi plus preparation and then a Z gate. For psi plus, we're going to do our phi plus preparation and then our X gate. I know there's a lot of terms here and it's kind of confusing to hear, but I hope this makes sense at some level. Okay, so let's go ahead and run our circuit. In the notebook, it shows how to run the circuit on the QASM simulator. This is the difference I was referring to. I'm going to go ahead and run it with the state vector simulator. But hopefully either way, this will be a good review of how this simulation stuff works. So remember that simulation always starts with selecting our simulator, which in Qiskit parlance is sometimes called a backend. So I'll do backend equals air.getBackend, and we tell it which one we want. In this case, we'll do the state vector simulator. Okay, then to run our quantum circuit, we're going to do a job equals execute. We want to try our circ psi plus, which was this one up here, comma, backend. Now, when we had the QASM simulator, we additionally specified the number of shots, not necessary for the state vector simulator because there's not even an effort to simulate randomness, right? It's just going to do some linear algebra for us and tell us what our output state should be. Once we've executed our job, we want to get our result. And then finally, we'll print out the state vector, which again is just result.getStateVector. Go ahead and run this. And we see our answer. So again, these can be a little bit hard to read. Just pay attention to where the commas are. That's going to be the best indicator of where your 4 elements are. And remember that the order here is in increasing binary counting order. So the first element is 0, 0, second element is 0, 1, third element is 1, 0, fourth element is 1, 1. So in this case, we see that we get a 50-50 superposition of 0, 1, and 1, 0, which is exactly what we were looking for with psi plus. So this works as expected. As I briefly mentioned before, I will show how to prepare the psi minus state in the optional content. For now, though, I will just tell you the answer, and I'll explain it later. Here we have a quick summary table of what we've learned so far. So if Alice wants to send, whoa. Okay, that was weird. If Alice wants to send 0, 0, she does nothing to her state because again, phi plus is the state they already had. If Alice wants to send 0, 1, I guess this is in a slightly different order than the way we did it, but if Alice wants to send 0, 1, she has to apply a Z gate to her qubit, and that's going to transform their phi plus state into phi minus. If she wants to send 1, 0, she's going to apply an X gate to her qubit, and that's going to transform their phi plus into a psi plus. And if she wants to send 1, 1, she is going to first apply the Z gate, then apply the X gate. So that's the answer to how you create psi minus. We'll talk more about it in the optional content. But yeah, she'll apply basically both of the gates, and then you get negative psi minus, which is a little bit of an annoying inconsistency. But remember, this negative is a global phase. As long as this is not a relative phase, it's not going to matter. So it is negative psi minus, but because that negative is just a global phase, it's basically transforming the state into psi minus. Okay, so this is a really good table to sort of have open as a reference because it tells you everything you need to know about the encode step, which in my opinion, the encode step, by far the most complicated one, right? Like thinking about how these circuits are modified, how you transform your entangled state from phi plus into something else, thinking about the message that Alice encodes. This is the most complicated step, but this table hopefully is a good summary of what's going on here. So somebody asks, how does the resulting state translate into the intended message? That's going to be step 5. So we will get there. I'll just say, hold on to that question for now. Okay, so the last piece before we move on to step 4 is kind of similar to the first step. We're going to put all of what we've learned into a function to make our lives easier later on. Okay, so I'm going to go ahead and give myself a code block here. And just like before, I'm going to start off by defining a Python function. This one we'll call specify state. Again, I'm going to take a circuit as the input. But here, I'm going to take one other piece of information. I'm going to take Alice's message. So this is going to be 0, 0, 0, 1, 1, 0, or 1, 1, depending on what Alice wants to send. And as we know, depending on what she wants to send, we're going to do different things to our circuit. Okay, so I'm going to just use if-else statements here. So if Alice's message equals 0, 0, that's our first case. But remember, in this case, we actually don't do anything. And so the command, I guess, in Python for don't do anything is just pass. Does nothing. Okay. Otherwise, if Alice's message is 0, 1, then as a reminder, we want to create phi plus, or sorry, phi minus. I'm already getting my terminology confused. We want to create phi minus here. And so we're going to do circ.z on the first qubit. Sorry, type higher. I promise I'll get used to this eventually. Otherwise, if Alice's message equals 1, 0, here we want to create psi plus. So I'm going to do circ.x on Alice's qubit. And otherwise, well, actually, I guess I'll do, just for clarity, if Alice's message is 1, 1, then we want to create psi minus. And so to do that, again, we're going to do an X gate first, and then a Z gate. OK, and just for our own sort of debugging, I'm going to put an else clause here. If we happen to send in a different message that we're not supposed to, I'll just print out invalid message. Cool. OK, so this is step 3, the encode step. Like I said, definitely the most complicated one, in my opinion. But again, at a high level, Alice is going to have some message she wants to transmit. And note, everything we do in this circuit is only done on Alice's qubit. So Alice and Bob don't need to be together anymore because we never have to do anything to Bob's qubit. Everything in this step is only happening to Alice's qubit. OK, so I'm going to go ahead and run this. Again, nothing's going to happen because I just defined a function. And this brings us to step 4. Now, in step 4, we have another qubit movement. So once Alice has done this encoding step, she's applied gates to her qubit, she's now going to send her qubit off to Bob. Again, nothing happens here in our circuit, kind of like step 2. So we're just going to use a barrier again. Now, before we move on to step 5, I am just going to do sort of a summary of where we're at now. And in order to do that, I'm going to test out our functions and draw the circuit so far. So I'm going to create a circuit called, say, circ test, quantum circuit with 2 qubits. OK, step 1. Step 1 is to create the phi plus state. We had a function for that, which was just create bell state, or sorry, create bell pair, I believe we called it. And then we pass in our circuit like this. And so remember, that function is going to take the circuit as an argument, and then it's going to go and apply our H gate and our C naught gate to create our bell pair. OK, step 2, Alice and Bob travel far apart. For that, we're just going to use a barrier. So circ test.barrier to remind ourselves of where this step occurs. Step 3. We are going to have Alice encode her message. Now, we had a function for this as well. We called it specify state. Again, we pass in our circuit as the first argument. And remember, we give a second argument, which is the message we want to transmit. So let's say, just as an example, I want to send Bob the message 0, 1. OK, and then finally, step 4 is another transmission. Alice is going to send her qubit to Bob. We're going to use another barrier for that. Again, these barriers, they're just visual reminders of where steps 2 and 4 happen. They don't actually do anything to our quantum circuit. So you could remove them if it's confusing. I'm hoping that it actually makes things clearer. Yeah, sorry, I keep forgetting about the type higher thing. I'm going to try and remember that. OK, and then final step here is I'm just going to draw to see what we have so far. We'll go ahead, run this. And here we go. So as I said, our barriers indicate where steps 2 and 4 are. So here you can visually see what each of the steps is doing. Step 1, state preparation, creates our phi plus state. It's the same circuit we saw 2 weeks ago. Step 2, Alice and Bob travel far apart. Nothing happens to our circuit, but we have a barrier here just to remind ourselves that that's where that step happens. Step 3 is Alice encodes her message. So this middle part is going to look different depending on which message Alice sends. Note, however, though, that no matter which message she sends, all the gates are going to be on her qubit. Nothing is ever going to happen to Bob's. Step 4, we have Alice send her qubit back to Bob. So now Bob has both of them. And that brings us to step 5, which is the final step, to decode the Bell measurement. So what we have now is Bob is in possession of 2 entangled qubits, and those qubits are in one of the 4 Bell states. Which Bell state they're in is going to tell Bob the message Alice sent. So our final step is to figure out some way for Bob to know with 100% certainty which entangled pair he has. Now, think about this for a moment, because quantum measurement being as it is, getting an answer 100% of the time is actually kind of difficult, right? Like a lot of the times we have probabilistic outcomes. We have things like, oh, well, 50% of the time you'll get 0, 50% of the time you'll get 1. Here, though, we want something that works 100% of the time. So how are we going to do that? If we just straight up measure Bob's 2 qubits, we're certainly not going to get the right answer, because think about, for example, phi plus and phi minus. Both of those give you a 50-50 chance of being 0, 0 or 1, 1, right? And again, we want something that works with 100% probability. So if Alice sent 0, 0, and there's a 50% chance Bob would get 1, 1 out of that, it's not going to be good enough. So we have to come up with a different approach. So there is a mathematical way you can walk through this, and I believe in lecture you looked at the math. I am not going to go over the math here because it's already been covered. Instead, I'm going to try and give you some intuition for why it works. Now, all of this is explained in words here. I'm not going to read over it verbatim. Instead, I'm going to sort of talk through it and use this picture as my reference. So if you think about all the possible circuits we could get, right? So this is what it looks like when Alice sends 0, 1. Maybe if she sends 1, 1, we get a circuit that looks like this. If she sends 0, 0, nothing happens, so on and so on. So you can see that it's always this middle part that's changing. But there's one part that always stays the same, right? This initial part, the H gate followed by the C0 gate, is always the same. So if that first section of the circuit is what takes us from 2 sort of unentangled qubits, right, 0, 0 at the beginning, and it creates something that's entangled, maybe doing them in reverse would bring us from something that's entangled to something that is unentangled. And indeed, you probably already know from lecture, that's exactly what we do. We just apply these gates in reverse. So we're going to tack on a C0 gate followed by an H gate, just reversing the order. And that's going to kind of undo our entanglement. It's going to take an entangled state and give us back ket 0 and ket 1s, which is exactly what we want. Okay, so final step then, let's go ahead and create a function for ourselves, kind of like before, that does what we call a Bell measurement. So oftentimes you'll hear this word used in general quantum computing literature, a Bell measurement. And a Bell measurement is sort of one term that describes this combined process of doing a C0, an H gate, and then your classical, and then your Z basis measurements. And sorry, I know I'm at time, but like I said, this is the final step. We don't have too much more to go. So I'm going to define my function called Bell measure, we'll call it. And again, it takes a circuit as the input. And like I said, the intuition here is just like we used HC0 to create entanglement, we're going to use the inverse of that, C0H, to undo the entanglement. So I'm going to do circ.cx, 0, 1, circ.h on 0. And then the final step for a Bell measurement is, of course, to do a measurement. So just like before, we'll do circ.measure. And here we remember we specify which qubit we're measuring and then which classical bit we want to save that measurement in. So I'm just going to keep things simple. Qubit 0 goes in classical bit 0. Qubit 1 goes in classical bit 1. Okay, so let me run this to save that function. So the final step of this lab is to test everything. I'm going to throw up one more table, though, just to sort of remind us of where we're at. Again, I didn't go through the math here. That was went through in lecture, and I'm happy to cover it again in the optional content if we want. But this Bell measurement circuit is going to do the following. If Bob receives the state on the left, he's going to measure these classical bits on the right. And you can see there's some reasoning in here about how the C0 gate affects things, how the H gate affects things, and then ultimately what your measurement is. So note that after you've done this C0 and H gate, you don't have any superpositions anymore. And so we're going to get our answers with 100% probability like we wanted. Okay, here we go. Let's do the full thing all in one code block and see how it works. So I'll give myself a code block and we will get going. First step, as always, is to create a quantum circuit. In this case, we're going to have 2 qubits. We're also going to do a measurement now, though. So I'm going to include our 2 classical bits. I'm also going to build this up incrementally. So I'll do a quick draw to show what we have so far. And here you can see we've got our 2 qubits and 2, even though it's kind of cut off, classical bits. Now, kind of like I did before in the recap, we're going to do step 1 is the function we created called create Bell pair. Step 2 is just a barrier, right? And that's just to indicate that Alice and Bob are going to travel far apart. And step 3 is our encoding function. So that was specify state. We pass in our circuit. And then for this one, I don't know, I guess I'll do 1, 1 as the message we're going to send. Okay, let's take a quick pause here and draw our circuit again. So I'm going to run this cell. We'll see what we have so far. So again, step 1 is over here. Step 2 is nothing. They just kind of move apart. Step 3 is to encode. Let's keep going. Step 4 is just another barrier where Alice sends her qubit back to Bob. And step 5 is the thing we just talked about, that Bell measurement. So we're going to do Bell measure. And again, we just pass in our circuit. If I run this, we will see our full superdense coding circuit right here. So again, we have step 1, 2, 3, 4, and 5 from left to right. And if you just look at this circuit, it looks pretty complicated, right? But hopefully, as we've broken it down into steps, you have some understanding of sort of what's happening at each stage of this circuit. So the only thing left to do is to simulate this and see if we get the correct answer. So again, the message that I've tried sending here is 1, 1. Let's see if that's what Bob gets. So for this one, I will use the QASM simulator because as a reminder, the state vector simulator doesn't deal very well with measurement, right? So now that we've got a circuit with measurements in it, we should probably use the QASM simulator. So we'll do again, error.getBackend. This time we want the QASM simulator. We will create our job by executing our circuit with that backend. Now we have to specify the number of shots. So I'll just do 1024 shots. Again, the number of shots just referring to how many times the quantum computer is going to simulate this. So it's going to try running this circuit 1,024 times. We expect that it's going to get the same answer every time, right? Because we expect that there's 100% probability of this working. We'll see if that's indeed what happens. We get our result like this. And then we're going to use our good old plot histogram function result.getCounts. Again, don't have to memorize these things. You can just look at previous notebooks to see how we do this. Okay, I will click run. And there we go. So what we're seeing here is that Bob measures 1, 1, 100% of the time. It's exactly what we wanted. Okay, so in the interest of time, I'm actually going to go over this difference between superdense coding and quantum teleportation in the optional content. It's not super necessary for the homework or anything, I don't believe. So I think I am going to wrap up the required content here just because I already am over time. And so I will go over the key takeaways. Like I said, superdense coding, tough to get your head around, but I really think it's worth spending some extra time if you need to really understand this algorithm, because it is going to set you up well for what we learn in the rest of the course. So high level, superdense coding allows Alice to send Bob a classical message consisting of 2 bits by transmitting only 1 qubit. So even though we've been working with a 2-qubit system this whole time, the magic of superdense coding is that Alice only has to send 1 qubit, right? Even though Bob's qubit is involved, Bob just holds on to it the whole time. We don't have to worry about transmitting it. As a high level of the sequence of steps here, in superdense coding, Alice prepares one of the 4 Bell states. So it always starts off with phi plus, and then Alice does some stuff to her qubit to transform that phi plus state into possibly one of the other 3, or she does nothing to keep it as phi plus. She then sends her qubit to Bob, and Bob is going to do a Bell measurement to figure out which of the 4 Bell states he is in possession of. And then the final point that I will talk about in a bit more detail during the optional content is that quantum teleportation is almost exactly just turning this whole circuit on its head, doing everything in reverse. Not quite, but we will talk about the differences in just a moment. As always, we have further reading and resources here at the bottom. All of these are great, of course. We'll go into our optional content, and there is extra optional content, as there will usually be going forward, which is strictly optional. You can go over this on your own, but I won't be covering it in labs. Okay, let me really quickly throw up the post-lab Zoom poll and hopefully wrap up fewer than 10 minutes late, which I guess would be pretty good for me, unfortunately. Okay, so let me go and start looking at questions. I think the way I'll do it today is I will spend, let's say, 15 minutes answering questions, and then I will go on to the optional content. Okay, so I think let me just try and find where I left off with questions. So somebody had a question about the if statement, right? So this was in our step number 3. Actually, sorry, before I start answering questions, I should wrap up the lab. That is the end of the required content. If you need to head out, feel free to do so. I do apologize for going overtime. Again, really try and work on cutting down these labs. But yeah, from here on out, I'm going to spend about 15 minutes answering questions in the chat, and then I will go on to the optional content, which, as a reminder, I'll be talking about quantum teleportation and preparation of the psi minus state. So if you have to head out, have a great week. I will see you again next week. For right now, I'm going to grab a quick drink, and then I'll come back to answer questions. Okay, cool. So I will go ahead and share the poll results for anybody who's interested. Okay, so yes, the student who is asking about the if statement. That was in our step number 3, entanglement. So they correctly point out that we could just totally remove this first part, right? If I just delete this first statement, I mean, by definition, it does nothing. I was just including it so it's sort of visually obvious that we have these 4 possibilities. But yeah, you could just do this, shortens your code, still works the exact same way. It's up to you which you prefer. Okay, so somebody asks, how does Alice send her qubit to Bob physically? So that's a great question. Transmitting qubits physically can be pretty hard, right? And this is one of the reasons I said superdense coding would probably not be used today, because transmitting classical bits of information is so much easier than transmitting qubits that you would be much better off to just transmit twice as many classical bits as trying to transmit qubits. Some ideas on how it can be done, though. It's, well, as with most things to do with quantum hardware and sort of the physical nature of quantum computers, it depends on what type of quantum computer you're using. The easiest one to explain and imagine is a photonic quantum computer. So a photonic quantum computer, each photon, which is just like a little unit of light. I think we talked about polarization super briefly in one of the previous labs. But a photon is a qubit, and you can literally send a photon down. It has to be a very good, but you can send it down a fiber optic cable. And there are ways of transmitting photons through fiber optics that don't destroy superpositions, that don't destroy entanglement. So that's one example. Photons would probably be one of the easier ones to transmit. If you want to get into transmitting, an ion, that might get quite a bit more difficult. To be honest with you, though, I don't know the details of how qubit transmission is actually done in practice. From what I understand, though, it's pretty hard. Okay, so somebody asked me to go over the Bell measure function once again. So let me go down to that. Yeah, so I guess there's two ways of understanding this, right? The most robust way is to just go through the math. And so my understanding is that the math was shown in this week's lecture content. And so, I mean, I guess I could go over it again if people are interested in that. But I think the only sort of addition I have to make on top of what was shown in the lecture is to try and give you some intuitive understanding for why this works. And in my mind, the intuition is simply that your initial HC0 gate creates phi plus. Swapping that around, doing a C0 H gate is going to sort of go the other way around. It transmits a phi plus into a 0, 0. It also just so happens that it translates phi minus to 0, 1, psi plus to 1, 0, and psi minus to 1, 1, which is obviously super convenient, right? But I think that an easy way to see it is to try and think about this sort of inverting business. Another thing you can do is, I think it was in this lab last week. I apologize if I'm getting that confused. But in one of my labs last week, somebody brought up the idea that you could use a different circuit to create phi plus, or sorry, to create phi minus. And the way that circuit worked was basically you apply an X gate right at the beginning. So you start off in the 1, 0 state, and then you do your standard H gate C0. And you do indeed get the same answer. So one way to think about this is that this HC0 thing, it translates one of the 2 qubit basis states into one of the Bell states. It also does that in reverse, right? So you can try this for yourself. Try the HC0 circuit, but instead of starting with 0, 0, start with 1, 0, or 0, 1, or 1, 1, and see what you get as the output. Okay. So somebody said I measured 0, 1. I think in your notebook, they might have transmitted a different message. So if I go back to my circuit here, you'll notice that I chose to transmit 1, 0. But if I chose to translate 0, 1 instead, that would be the answer I get. So I could just go ahead and change this. I have to remember to rerun this cell to update the circuit. And so you'll see here the gates in the middle, the gates in the middle of our 2 barriers that changed because now we're transmitting a different message. And then I can go down here and re-execute my simulation. And we'll see that we measure, as expected, 0, 1, 100% of the time. So somebody says, how do we get an arbitrary message instead of specifying it ourselves? So yeah, that's a good question. I guess the way that we have written things here, it's it's obvious to us what the message should be, right? We tell it that it should be 0, 1, and boom, like magic, we get 0, 1 out the other end. Maybe not all that interesting. But one way that you can sort of imagine this, actually, I think I can annotate on my screen here, I think, somehow. Maybe not. Okay. I'm not sure how the permissions are set up. But one way that you can think about this is to basically sort of like imagine the circuit bending up after this second barrier and going off somewhere far away, right? So you could even imagine that the circuit goes out of our view and someone somewhere is going to apply some gates and then send this qubit back, right? We don't necessarily know what gates were applied here. And so the whole idea with superdense coding is that Bob doesn't necessarily know what message Alice is encoding, right? Because again, Bob only has this qubit. What happens to Alice's qubit, qubit 0, in between these two barriers? Bob has no idea. And so the only way for Bob to get the message out is using this Bell measure and sort of this whole superdense coding protocol. Okay, can you please tell how Alice's qubit combined with Bob's qubit in step 5? Yeah, good question. So their two qubits were always entangled, right? Throughout this whole process, they are entangled. The interesting thing about entanglement is that distance, right, separating your two qubits does not break entanglement. Even if your two qubits are, you've probably heard this, but even if your two qubits are on opposite sides of the galaxy, they will still be entangled, at least in theory. So here, the two qubits are always entangled. They're always combined in some sense. We're just moving them physically apart and then bringing them physically together. There's no thing you have to do to them to recombine them when Bob gets Alice's qubit. When Bob gets Alice's qubit, they're still entangled. They're still combined with each other. He doesn't have to do anything extra. So somebody asks, can entanglement be broken by superdense coding? So I think the short answer to that is no, right? So we have an entangled state throughout this whole circuit, right up until we measure it, or I guess I should say right up until this Bell measurement, everything is entangled. And the whole process of superdense coding, steps 1 through 4, basically, they don't break the entanglement, right? The state remains entangled throughout this whole process. So to the question, can entanglement be broken by superdense coding? The whole point is that it's not, right? If our protocol here somehow broke the entanglement, this would no longer be possible. The magic of superdense coding rests on the fact that these two qubits are entangled for the whole process. Okay. So I see a few people saying that like Alice's qubit does not get sent back to Bob. I think this is a misconception, if I'm understanding this correctly. So Alice's and Bob's qubits are physically separated, right? So like Bob always has his qubit. Alice is going to keep hers at the beginning and send it to Bob, physically send it somehow, whether it's down a fiber optic or, I don't know, in a parcel with some kind of souped up atom container thing, whatever. There is a process in step 4 of physically sending Alice's qubit to Bob. Bob's qubit, he always has it. It never changes hands. But Alice, she does have to send hers. Okay, so let's see. Somebody asks in a direct message, if I want to send the original message that we had for ice cream, 1100 or 1, whatever it was, I forget. If you want to send that all at a time, all at once, how can you do it by just modifying the code done before? So the way that you would send a longer message like that is you would have multiple sets of entangled pairs, right? So you would basically just copy paste this exact circuit. So instead of having 2 qubits for an 8 classical bit message, you would need 8 qubits, 4 of which are going to be transmitted. And each pair of qubits is responsible for transmitting 2 of the classical bits of information from your message. So to translate a longer thing, you can effectively think of it as just repeating this process once for every pair of classical bits. Okay, so somebody says, so the entangled state is like a secured pipeline for sending a message. Do I understand it correctly? So that's a great question. Off the top of my head, I believe you're right that this is a secure channel. I'm not sure though. I haven't actually checked that. What we mean here by a secured channel, though, is starting to dip our toes into cryptography a little bit. And it basically means if we have some attack, like malicious person who wants to figure out what message is being sent to Bob here, could they do it without Alice and Bob knowing? Right? So in the world of classical computers, the answer is yes. And that's why we need all of these sort of internet security protocols to try and hide our message, or encrypt it, as it's called, before we even send it. But here, Alice and Bob aren't encrypting their message. They're literally just sending what they wanted to send, right? And so the question then becomes, could somebody intercept that, figure out what message was sent without Alice and Bob knowing? I think the answer to that is no. And so I think this does count as a secure channel, but don't quote me on that. The whole world of figuring out sort of quantum cryptography and how you transmit messages in a quantum safe way is super interesting. It's very fascinating. And this example with superdense coding, Alice and Bob transmitting between each other, is kind of like the, I guess, the foundation of pretty much every quantum cryptography protocol. So I don't know off the top of my head if we are going to learn more of them in this course, but certainly you could go off and read some of them yourself with this knowledge for sure. Okay, so let's see. When creating the 1-1 state, does the order of Z and X matter for step 3? That is a fantastic question. So let me go back to the encoding step. Oops, what did I pass here? Oh yeah. Okay, so here in our table of encodings, the way that I wrote it was, oh, actually, I think I was inconsistent, wasn't I? The way that I coded it and the way it's written here. So the way it's written here, remember, matrices are applied in sort of reverse order. So as it's written here, we would apply the Z gate first and then the X gate. And then we would get negative psi minus. If you flip these, if you apply X first and then Z, you still get psi minus, but you don't get the global phase. You would actually get exactly psi minus. The way we presented it here like this is just because that's what was in lecture. But the reality is you can do it in either way. The algorithm still works the same. It doesn't actually matter. So fantastic eye there. That's not obvious, I don't think, at first glance, but it's true. The order here does not matter. Okay, so somebody direct messaged me. Could you elaborate? How would Alice actually send the state of the qubit? Suppose she did apply the gates to her qubit. How would she know what to send physically? So as I sort of said before, this depends on what type of quantum computing you're using to do this algorithm. If you're using photons for your qubits, then you can send them down a fiber optic cable. If you're using ions as your qubits, things get a bit more complicated. But at the end of the day, to make superdense coding work, you do need some kind of physical transportation. You need to move your qubits somehow in the real world from Alice to Bob. So I honestly don't know how to elaborate on it more than that. Like I said, I don't really know the specifics of how physical transport is usually done, but there does need to be that step for superdense coding to work. Oh, oops, that same person sent me a clarification. Maybe I should read that. What I mean was, how is it even going to be possible in principle? Won't we have to know? Oh, I see what you're saying. Yeah, okay. So they're saying, how do you send a qubit if you don't know the qubit state, right? To figure out the qubit state, in theory, we'd have to measure it, which would collapse our superposition. And then, we can no longer have a qubit to send. So here, we're talking about sending the qubit without necessarily knowing the exact state that we're in. In this case, we happen to know exactly what state we're in, right? Alice will know precisely the state of her and Bob's qubits. But here we're just talking about physically transmitting a thing, right? So maybe in this case, the easiest way to think about it is with ions. So you start off with two ions next to each other, and you shine some kind of laser on them that's going to make them entangled and create a phi plus state. Then you physically take this ion, ship it off somewhere else to Bob, for example, or I guess Alice and Bob take their ions to different parts of the world. They haven't measured their qubits, right? Their qubits are still just ions in an entangled superposition. Then they can still do quantum gates to them because they haven't measured anything. They haven't collapsed the superpositions. And Alice is just going to literally send that atom to Bob, right? So there's no measurement, nothing like that. It's a physical transmission of that actual object in real life that is representing our qubit. So in this case, it'd be like an ion that you're sending to Bob. So you're right that if Alice measured her qubit, that would break everything, right? Our entanglement would be gone, the superpositions would collapse, the algorithm wouldn't work anymore. So you don't measure anything until the very end. Bob is the only one who measures. Okay, so yeah, low altitude satellites, that works too. Any transmission method that actually is able to transmit a qubit works for this. So I'm seeing the same question sent again. How do we get an arbitrary message instead of specifying it ourselves in the code? So I think that's just me. Oops. Let me go back down to our final example here at the very, very end. So I think this was me just maybe not explaining this as well as I could. So this message can be anything we want, right? I can change this to be 1 1 0 0 0 1 1 0. And if I just rerun this circuit, we will see what Alice should be doing to her qubit to transmit each of those different messages. So this is any arbitrary message you want. You can pass in anything here and it should work. Well, any 2 classical bit message, I should say. And it should work as expected. Okay, so somebody says a little bit out of scope possibly, but can you explain how do you actually put a qubit in a superposition physically? What is the mechanism behind that? So I am going to keep answering questions that are more relevant for now, but I'll cover that toward the end. I'm just going to copy paste your question into a notebook. Cool. Okay, what is the difference between the circuit sending 3 or more qubits of information compared to this one? Is it just more effort on the specification of the message correction, or I'll have to do something else? So again, if you wanted to apply this to a larger message, you literally just copy paste the same circuit for each pair of classical bits in your message. And then it works the same way. So I would think of it as just if you had a 8-bit message, for example, you run this exact procedure for the first 2 bits, you run this exact procedure for the second 2 bits, and so on and so on. And so at the end of the day, for each copy of this circuit, Alice is going to have to send Bob 1 qubit. And so in total, you'd be sending Bob 4 qubits for an 8 classical bit message. Why does this sound similar to symmetric key encryption? Probably because it's inspired by the same kind of math. A lot of the early research in quantum computing was based on cryptography. And a lot of the early researchers in quantum computing were like combinatorics and optimization people. So indeed, a lot of earlier quantum algorithms are heavily inspired by classical cryptography as well. Okay, so somebody says, I think I'll answer one more question and then I'll do the optional content. But then hopefully I'll get back to questions after that. So this question, suppose Alice did apply the gates to her qubit, how would she know what to send physically? What I mean is, how is it even going to be possible in principle? Oh, wait, sorry, that's the same question. I think I already answered that. Okay. Okay, so if we want to send 6 bits of classical info via 3 message Alice qubits, I still would only need, oh, I see what you're saying. Yeah, okay. So they're asking if you wanted to send, in this example, 6 classical bits, would you need 3 qubits with Alice and 1 with Bob? Or would you need 3 qubits with Alice and 3 qubits with Bob? As we've described it here, you need 3 qubits with Alice and 3 qubits with Bob, right? So it's literally take this exact same circuit, both qubits, everything about it, and copy paste that however many times you need to send your message. So for a 6 classical bit message, you would need 6 qubits total. 3 of them go to Alice, 3 of them go to Bob. But the key with superdense coding is that now only 3 of them have to be transmitted instead of needing to transmit 6. You still need 6 qubits total, though. Okay, so I think I'm going to stop there for now and do the optional content, and then I will come back to questions. Oh, okay, so first part of optional content, I guess I skipped over, was the difference between superdense coding and quantum teleportation. So what we taught you here is obviously superdense coding. Quantum teleportation is effectively the reverse. So I really like this little table down here as a good summary. So superdense coding, what we just learned, is transmitting 2 classical bits using just 1 qubit. And I guess maybe using isn't the best word. It's transmitting 2 classical bits by transmitting 1 qubit, right? As we see, you still have to use 2 qubits, but only one of them is transmitted. In quantum teleportation, it's exactly flipped. You transmit 1 qubit using 2 classical bits. So quantum teleportation arguably, and again, arguably, because all of quantum computing is still very new right now, quantum teleportation is arguably more useful because transmitting classical bits is usually easier than transmitting a qubit, right? And so teleportation is the inverse, because in superdense coding, we are transmitting a physical qubit to tell Bob about 2 classical bits. In teleportation, we are physically transmitting 2 classical bits. So those could be like pulses down a wire, like voltages down a wire or something like that, in order to tell Bob about 1 qubit. And so that's why it's called teleportation. It's a bit of a, I think it's a bit of a misnomer, because you still have to send these 2 classical bits of information for Bob to know exactly what state Alice wants to send. In general, though, I think one key takeaway from both of these algorithms, superdense coding and teleportation, is just the idea that a qubit, fundamentally speaking, seems to have about 2 bits of information stored inside of it, right? When we want to transmit 2 classical bits of information, we only have to send 1 qubit. If we want to transmit 1 qubit, we have to send 2 classical bits, right? So it always takes twice as many classical bits to kind of do anything as you would need with qubits. Now, I believe, well, I'm not sure if we've actually given you more resources on quantum teleportation. Having seen superdense coding, I honestly think you could just look at the Wikipedia page and you would be able to figure out what's going on. It is basically just the same circuit flipped around. So instead of starting off with encoding a qubit and sending that qubit, we're going to start off by measuring a certain state, sending the results of that measurement, and using those results to reconstruct the state. So again, I won't go into more detail on it here, but it is pretty much the same as what we just learned. Okay, let me just see. Okay. Yeah, I'm just looking at the chat one more time. I will go back up to look at the previous messages, but looking at the chat again, somebody said, thanks for the clarification. 1 qubit is transmitted, but you still need 2. Exactly. And I would say, like I said, this wording is a little bit misleading maybe. I would phrase it as you transmit 2 classical bits by transmitting 1 qubit, even though you still need 2. Okay, so that is what I missed in the required content. Let's go on to the actual optional content now, which I actually think should be a pretty straightforward extension to what we've seen before. So here we're going to talk about how you create the psi- state. Now, I briefly said before that this was going to be a combination of an X and a Z gate. So let's go ahead and see that in action, and let's basically just confirm that this works the way we expect. So I'm going to give myself a code block here, and I'm going to create a circ psi minus quantum circuit with 2 qubits. We're not going to do any measurement here. I just want to check that the circuit we came up with earlier really does do what we need. Okay, so what we're going to do then is we're going to do circ psi minus dot h on the first qubit. You should be getting used to this particular sequence of commands by now, h and then a C0 gate. And then I'm actually just going to do circ.draw to check where we're at so far. Okay, so this is our phi plus, right, that we usually have. Now to construct our psi minus, we said that we are going to do an X and then a Z gate. Again, the order here doesn't actually matter, but I will do it in this particular order. And actually, why don't, just as an exercise, we'll try it in the reverse order just to prove to you that it works both ways. But first, let's do X and then Z. So we get this particular circuit. Now let me give myself another one to run the state vector simulator. Backend equals backend. So here we're going to use the state vector simulator. This should all look pretty familiar. We're going to execute our circ psi minus with that backend. No shots because this is not the QASM simulator. We get our result like this. And then I'm going to do result.get state vector. Sorry, typing again. All right. So if I go ahead and run this. Okay, so let's take a look at what we have here. Again, our 4 elements are 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, and 1, 1 are both 0. That is as expected because psi minus, as a reminder, should be, I think we wrote it up here, yes, 0, 1 minus 1, 0. Now, unfortunately, that's not quite what we got here, right? What we really got is minus 0, 1 plus 1, 0. Again, though, that's just a global phase. I could multiply this whole state vector by minus 1, and I would get exactly psi minus. And so because this is a global phase, it doesn't matter. Because we can multiply the whole vector by one number and get the thing we want, it doesn't matter. Let's go ahead and swap these 2 gates, though. So suppose we did it in the other order. We're going to do Z then X. So again, just watch this circuit. The only thing that changes, boom, the order of those 2 gates. Okay, let's go ahead and run that again. And here you'll see we get almost the exact same answer, but now we got precisely what we want. We actually get exactly psi minus instead of that negative psi minus business. So again, global phase doesn't matter. So the previous one works. This one, I think, is honestly even a little bit more clean because it gives you exactly psi minus, which just fits the narrative a little bit nicer. Okay, so that's all I had to say on optional content. Let me quickly check for any questions on that optional content, and then I'll get back to questions. So somebody says, you explained that to encode, Alice uses the Z gate, but during the lecture, it was mentioned that the X gate is used. Yeah, so let me clarify. Alice uses either the Z gate or the X gate or both to encode. It depends on what message she is sending. So if we go back up to our step 3 function up here, she will use Z, X, or a combination of the 2, depending on what message she wants to send. So again, in this lab, I've used a couple different examples. I think I sent 0, 1 at one point. I sent 1, 1 at another point. That's just all that's mattering here. Oh, I know what you're referring to. Sorry. Okay. Yes, I think I forgot to mention that, and I definitely should have. In lecture, I was told about this. In lecture, they used left indexing. So yeah, I apologize. That's a bit of a confusing point. Because we're in Qiskit here, we have to use right indexing. Qiskit sort of commands that you will use right indexing. But in lecture, I think you used left indexing. The difference there is that these messages, 1, 0, and 0, 1, are swapped, right? So for 1, 0, you would have used Z, and for 0, 1, you would have used X. The algorithm is still the same, but because of that difference in indexing, gosh, I don't know why it's doing this. Because of that difference in indexing, you have a different convention for when you apply X or Z. The rest of the algorithm works the exact same way. But for example, for homework and that kind of thing, I hope that they just tell you which way it should be done. Otherwise, ask on Piazza, because this is just a convention thing. Different textbooks, obviously, apparently, different lecturers and lab people are going to use different conventions, which is, as somebody says, kind of annoying. I agree. Okay, so let me return to some of the questions that were being asked before. Okay. I think I answered that one. Sorry, I'm just getting caught up to where I was. So yeah, somebody asks a question. If the two qubits are entangled, so Alice's and Bob's qubits are entangled, even though we separated them or moved them away, so that's correct, right? They remain entangled even when you move them away. Then why does Alice need to send her qubit to Bob? They're already entangled, right? That's a great question. And indeed, in some quantum cryptography protocols, for example, quantum teleportation, you don't need to transport your actual qubit, right? There's other ways of exploiting that entanglement to transfer information. Here, though, the way that we've set things up, I guess to answer your question, I would say, think about what Bob has, right? So here, let's look at our full circuit again. If Bob just has his qubit, what information can he possibly get from that, right? And I guess there's no easy way to prove that this is impossible. Well, there is a way you can prove this is impossible, but it's not something we've really covered in this course. Instead, you can just try and work through, if Bob just has this one qubit, he can apply gates to it, he can measure it all he wants, but anything you try should always give you a superposition. And well, actually, there's a couple of problems. Anything you try is only going to give you one bit of information, right? Because at the end of the day, Bob has to measure. And when you measure in the Z basis, you only get one bit of information. The second problem, though, is that you are always going to get a superposition. And so again, we want something that works with 100% probability. A superposition is not going to work for that. Okay, so somebody says, is it because of the computation and the initial state known that made Alice know what state the qubit is in? So I guess, yeah, it's required that Alice knows the two qubits start in the 0, 0 state here. So if you don't know what your two qubits are, then this will not work. But for Qiskit and for the way that the algorithm is defined, we assume that we start off with two qubits and we know that they are in the 0, 0 state. So somebody says that they're having an issue uploading the Jupyter notebooks today and last week's is gone. Huh. My gut feeling is like maybe this is an issue with this new UI that they've done. Yeah, I don't know if anybody responded below if this is an issue for them as well. But yeah, my recommendation would be email student@qubitbyqubit.org, and they should be able to help you out. Oh, I see. Okay, so this person who was asking, yeah, they clarified their question. They were just saying, for fun, how would you just pass in a random message here? So I guess there's a couple of different ways to do this. This is just a Python question, though, right? You want to generate a random 2-bit string. You can Google how to do that. Off the top of my head, I guess one way to do it would be this. So I'll need to import random. And then you can use, I'm almost certain there's a better way to do this, but you can use this function called random.choice, which pretty much as it sounds, gives you a random choice. So I'm going to do a random choice of 0 or 1. And then I'm going to string concatenate that. So remember, we talked about concatenation in one of our first programming labs. Another choice between 0 and 1. So I think this will work. Let's try it and see. Yep. So there we get an X gate. We run it again. Oops. That's not what I wanted. I want to run this one again. Then we get no gates. Yeah, so this should work if you wanted to just plug in something random. And to make this a real mystery for ourselves, we could not draw the circuit, generate some random circuit. This is, I guess, more similar to what would really happen, right? From Bob's perspective, he doesn't know what Alice has done. So we do some random circuit, and then Bob only has this measurement step to figure it out. And it turns out here, Alice sent us a 1, 0. Okay, cool. I'm glad that person figured out how to upload the notebook. Okay, so somebody said, you said we have to send half the number of qubits compared to classical bits. But to be entangled, you have to create both qubits from the same source and then send the qubits to sender and receiver. And now we're sending qubits again from Alice to Bob. Isn't it similar to sending 500 megabytes twice? Yeah, this is a fair point. And so this is kind of why I don't like the Charlie interpretation, right? Because when you describe it using Charlie, Charlie sends 2 qubits and then Alice has to send a qubit a third time, and it just seems totally wrong, right? I think the best way to sort of understand why this is useful and helpful, though, let me put back our circuit here. Well, okay, let me give us something that's non-zero, hopefully non-zero. Okay, there we go. So let's look at our circuit here, right? I think the easiest way to sort of understand this, because we do have a lot of qubit transport going on, right? You're totally correct that Alice and Bob, as I described the first step, when I said they move apart, well, isn't that actually both of them moving their qubits? And isn't that just as bad as sending 2 classical bits, right? I totally understand that interpretation, and it's a valid point. What I would say here, though, is that in theory, these steps can be separated in time, right? So Alice and Bob might be together at some point in time, move away, and then at some point way in the future, maybe they need to get a message to each other really quickly or really efficiently. So you're kind of loading all of the information transmission into your last qubit transfer. I don't know if this is actually helpful, but like, I guess this is the reason it's called super dense coding. It's because you're packing more information into that 1 qubit that you send, right? Alice and Bob don't have to know Alice's message when they do the first 2 movements. They only have to know the message before Alice's third and final movement. Yeah, I don't know. At the end of the day, like, your point is valid. I agree. But hopefully that gives some intuition for why we might care about this anyway. Yeah, okay, so I explained the difference in encoding for 0, 1, and 1, 0. Why do we have measurement blocks for both qubits in our notebook? Well, I guess you need both measurements to do the Bell measurement, right? And to get 2 classical bits of information, you need to measure both qubits. I'm not exactly sure if that's the question you're asking, though. So if I didn't answer your question, feel free to rephrase. Yeah, I'm sorry for the inconsistency between lecture and lab notation. I agree, it's kind of annoying. At the end of the day, though, like, well, I do wish we, in this particular case, I wish we had done a better job of remaining consistent. But in future studies, and if you start reading things more on your own, there are unfortunately inconsistencies, and they are confusing. So in some ways, it's good to get used to that now. But yeah, it's annoying. Okay, so I think I've hit the end of all the questions. Does anybody else have anything they want me to talk about? Oh, actually, wait, somebody said this out of scope question from earlier. Can you explain how do you actually put a qubit in a superposition physically? What's the mechanism behind it? So I can explain this for one example, right? Again, it depends on the type of hardware that you're using. So The type of hardware I'm most familiar with is what we call cold atom computers or neutral atom computers, which is basically your qubits are atoms. They're not ions, though. They are just, as the name suggests, neutral atoms. Now, to create a superposition for neutral atoms, I guess I should first explain, your qubit is the state of your electron. So if you've learned about orbitals in a chemistry class or a physics class, your different states for your qubit are different orbitals that the electron sits in. So visually, let me see. Oh no, I still can't draw on this. Okay. For this question, I'm just going to switch back to my slides real quick so I can draw. Let me just do this on the side here. So you might have seen, even though, as I've said before, this is an inaccurate drawing, it is fair for this case to think of an atom as just a nucleus and then several sort of circles around it. So for this case, I'll just draw two circles. And basically, the way that a computer works in this case is you start with ket 0 being the electron flying around this orbital, and ket 1 being the electron flying around this orbital. Then the first question, I guess, before we get to superpositions, is how do you sort of move between ket 0 and ket 1? Now, this is also going a little bit into physics, but there is an energy difference between these two. So it actually takes more energy for the electron to stay in what we call a higher orbital, right? So these orbitals that are further out from the center are higher orbitals. It takes more energy. Now, one of the interesting results from quantum mechanics or quantum physics is that sort of moving an electron from one orbital to the next, you need to give it a precise wavelength, a precise amount of energy. And the energy you pump into it has to be exactly equal to the difference between those two energy levels. So, say here that it has, I don't know, I guess I can say energy just in joules, right? If it's got like 1 joule of energy here, 2 joules of energy here, you need to hit it with a laser that is exactly 1 joule of energy. So you do that by just changing the wavelength. Now, to create a superposition, you can hit it with, well, actually, okay, now that I'm halfway into this, I think this might take more explanation than I'm prepared to give. I guess one way you can think about it, though, even though this is not actually technically correct, is hitting it with a laser that is, instead of like 1 joule of energy, 0.5 joules. And so that kind of moves your electron somewhere halfway in between your two orbitals. And then whether it falls back to 0 or goes up to 1 is a 50-50 chance. Again, that's not exactly how it works, because in this case, it would not go up to 1. There's no chance it would do that. But you can sort of do some tricks with your lasers that create this effect where it will either fall back to 0 or 1 with equal probability. Well, actually, I guess I can quickly explain it. Sorry, and by the way, for anybody listening to this, this is 100% optional content. You don't need to know this for the course. Usually the way this is done is by exciting your electron to a way higher electron orbital. So, if I change the scale on this a little bit, maybe our first two orbitals were like down here. Right, something like this. And then we have some other big orbital. So this orbital up here is like super high energy compared to the other two, right? Because it's way further out. And so what we would actually do is we would raise our qubit with a super energetic pulse of light. We would raise it up to this super high state, right? So it'd be super energetic. And then as soon as we turn off the laser, it's going to rapidly lose that energy. But whether it loses the energy, and this is what we call decay, so whether it decays down to the ket 1 state or back to the ket 0 state is basically random, right? 50-50 chance. And so when we do this sort of superposition creation, what we're actually doing is we're setting it up in this highly energetic state. And then as it decays, it puts itself into a superposition of 0 and 1. So I guess going back to the original question, which is just how do you physically create superpositions? at the end of the day, it often comes down to physics, right? You have to understand some physics of the system you're working with to understand how these superpositions are created. But this is one idea that I think you can get at least the core concept of by thinking about electron orbitals. So hopefully that helps a little bit. Cool. Okay, and I will say as well, I believe Amir, like lecturer Amir, is planning on doing a couple of lectures toward the end of the course on various types of quantum hardware. I personally think that will help with answering a lot of these kinds of questions because, I mean, the reason we don't teach these things in this course is that they often do require quite a bit of physics background. So, if you wanted to go into quantum hardware, you do have to learn physics at a decently high level. But quantum computing and quantum algorithms is way bigger than that, right? And so you can learn these concepts without knowing all of the hardcore physics involved with it. That being said, though, I think it's even possible to learn some of the hardware stuff without all of the physics formalisms. Even what I described here is that's pretty much enough for what I do, right? I work on quantum hardware. I don't really need to understand in much more detail than this. So at the end of the day, I think a lot of these things are overcomplicated in universities. And so hopefully we can do a little bit to help with understanding without going into all the crazy math of it. All right, so I think I will wrap things up there. Thank you everyone who's still here for sticking it out till the end. As usual, I will post this up on YouTube and send out an announcement later on today. Have a great week, everyone, and we'll see you again next Tuesday.